questions?
Remember I told you when I was like just weighing when I was weighing the equipment by myself and the scale kept going down, if it was only the last two decimal places, so like the ending two, would that affect the percentage error a lot, or would it not because it's the last two?
Not that much.
Okay.
It's not going to impact it.
Okay. That's what I was conditional.
Yeah, the question was regarding the balance. Did you guys experience any drift in the balance? The mass just wouldn't stabilize? Different reasons for that. Evaporation on the surface. This is why they say dry the outside. Make sure it's dry. You could have surface evaporation on the outside. There are other things that could cause the drift as well. It's very annoying when you get drift, when you don't have... This is the problem. When you have things, very sensitive balances, then it opens up a whole new world of headaches. Versus using the centigram, did you ever experience any drift with the centigram? Not so easy, right?
I'm pretty sure I lost a few grams myself other than that.
Yeah. So now that's it's one of those things. Other questions? So what do densities usually range from, let's say? Densities usually range from like 0.001 grams per milliliter. That would be the density of what? If I had a density of 0.001 grams per milliliter, a lot of people don't like decimal places. So rather than writing 0.001 grams per milliliter, they'll do this per liter instead, or they'll do milligrams per milliliter. This would be 1 milligram per milliliter, or 1 gram per liter. And so we could use lots of different units for this kind of stuff. But that would be the density of what? Is that a light density or a heavy density?
Very light.
Yeah, it's very light, so it's got to be what?
Gas.
A gas. So this is the typical density of a gas. And are we going to have, this is 1/1000th of a gram per milliliter. Are we going to have something like 1,000 grams? Like a kilogram per milliliter?
Are you recording this?
Yeah. Okay. Thanks. How extreme does it go? Are we going to have something like 10,000 grams per milliliter? What do you think? About, what would you expect for a reasonable range in densities?
Maybe like 0.1 to 10. Depends on what we're working with.
Yeah, it depends on what we're working with. So, what's the most dense thing you can think of?
Star, neutron star or something.
Okay. Yeah, or like a nucleus. You know the density of a nucleus? Density of a I calculated before, but it's been a while since I calculated. It's like something around 2,000 tons per cubic milliliter. Or not, is there such thing as a cubic milliliter? No. 2,000 tons per milliliter. That's because atoms are mostly empty space, but if you look at just the nucleus, well, that's not empty space.
So for the nucleus, remind me, when would you use angstrom?
We use angstroms. It's just another unit. It's like one would use liters rather than milliliters, just whenever it's convenient. And so people still use, although there's a movement to get rid of the angstrom, people still use the angstrom. Well, especially when they're talking about, actually, let me turn this on. Wavelengths of light. And not only that, angstroms are used to describe the size of atoms. And so we use angstroms when we're talking about the size of atoms or wavelength of light.
Because that's what the mass spectrometer is using, right?
That's what the mass spectrometer is using for what?
To measure the atom.
No.
No. What is the mass spectrometer?
The mass spectrometer on the y-axis is the intensity or the number. The more atoms that hit a particular point, the higher the intensity. The fewer the atoms that hit, the lower the intensity. And so the intensity tells us the percent, what, blank, blank, percent abundance, or percent natural abundance of the natural sample. And then on the x-axis is what?
Isotopes.
On the x-axis is the mass. The usual units of mass would be U.
So would the mass be the range then? Because I saw a graph that's had on the x-axis a range.
Yeah, for the isotopes. Do you expect an infinite range for isotopes? You know, all the isotopes are going to cluster around a certain number. So, if I'm looking at carbon, let's say this is carbon 12, you know, would you expect a carbon 57 to exist? Or is that kind of pushing the range envelope a bit?
Pushing it.
It's pushing it. You'd expect all the isotopes to cluster around 12. So there's carbon 13, there's carbon 14. That could be the range of isotopes that are observed for a particular element. You know, lead has more peaks. So, in that sense, but we don't normally call it a range. You know, when we look at the table of isotopes, then the range that you'd be describing is this. What are the ranges of isotopes for carbon? At least on this table, it would be 12 to 14. You know. For oxygen, it would be 16 through 18. There are radioactive isotopes which are going to extend the range. And so there's actually a carbon 15, etc. You know, but there's a limit to how far it goes out because you know it's just terribly unstable. The same thing for density. You know, there's a range that we kind of expect for the density, and the range is going to be from gases to solids. And so what are some of the most dense solids you can think of? Osmium and iridium. And about how dense are they? Like 26, 25? How about 1,000 grams per milliliter? Would you expect that to be reasonable? How about 500 grams per milliliter? Reasonable? 818 grams per milliliter. Reasonable? No, those are outside this range, and this range that we have is a range that we kind of memorized. This is part of the, you know, the two-pronged approach to chemistry. You know, theoretical and empirical, and that is observation or factual memorization. So we kind of memorize a range. You know. For some of these, we don't want to memorize a range, you know. We just know that the isotopes are going to cluster around one another. We don't see extremes. So it doesn't go 20, 21, 50 for neon, right? They all cluster around. And so I told you the density table for water is a bit tricky. And so every semester somebody tells me that the density of water is 818 grams per milliliter, but what has a density of 818 grams per milliliter? Is that in the reasonable range? No, that's outside the reasonable range. And so what we want to do is we want to have something that's reasonable. And so knowing that, And knowing that the density of water is around 1 gram per milliliter means that that table's weird. The table's weird because the table is just trying to minimize the amount of repetitive work that you have to do. If you were to make that table by hand, you'd have to write, this. So let me just talk about the table. The question about the density table. And I just had it up here. Where did I put it? There it is. Just show me the table. So you might have figured it out. That table's being lazy. Whoever made that table is lazy. Why? The person who made that table is lazy because they didn't want to rewrite 0.999, 0.999. If you look at these first 5, 6 measurements here, 999, 999, 999, 999, just what changed? The last 4 digits changed. That's it. And so rather than rewriting 999 every single time, they didn't, and then they waited until it changed. Going from 15 to 16, it changed here. And so what they did was they didn't write this and left it blank. And so it went from 999,702, 6 to 999,6084. So the density dropped a little bit. But that doesn't mean the density is 6,084 or 608.4 or whatever. That's often done, you know. But usually people put a little, like a quotation mark there, to show that it is. So, but like I said, part of science is trying to recognize a pattern. So maybe you see it, maybe not. But okay, to answer the question on the density table is, if it's blank, then you look for the first 3 digits. And so if I just saw 1026, I look for the first 3 digits up, unless there's an asterisk. If there's an asterisk, because they made the column width too small. If there's an asterisk, that means look for the first 3 digits past. And so if there's no asterisk, you look for the first 3 digits before. If there's an asterisk, you look for the first 3 digits after that particular entry. Does that make sense? And so that's what's going on with that table. All right, other questions? Now, it's a bit confusing on the report sheet. On the report sheet, it has percent error. What was the purpose of Part A, though? Was the purpose of Part A to figure out what the volume is? If the purpose of Part A was to figure out what the volume, then why did we bother measuring the mass? And why did we bother calculating the density? And so the purpose of Part A was to figure out the density. And so what they're asking is, they want to compare the theoretical density. The theoretical density is off the chart here. And so what was the temperature of the water?
I got 17.5.
Yeah, pretty cold. 17.5. We look it up. That's the theoretical density off the chart. And then we compare that to the experimental density. The experimental density is, we measured the masses, and then we figured out the mass of water by subtracting. And then we measured the volumes, and then we figured out the volume of the water by subtracting. And then we could take the mass to volume ratio, which is the density, and that's what we call our experimental density. And so the percent error is the experimental density that we got from our experiment, minus the theoretical density that we got from the table, divided by the theoretical density times 100%. That would be the percent error. Okay. Any other questions?
So I was a little confused on how to find the percent error. So like I couldn't find theoretical.
For the density of water?
I think it was, yeah, it was the one with the more pipette. Do you have the?
What was your temperature?
My temperature was 17.5 degrees Celsius, but where I was getting confused was.
I'll tell you what your theoretical is. You want me to tell you what your theoretical is?
Yes, please.
This one is only 5 sig figs. And this one, they weren't lazy. They ended up writing the first 3, but it takes up more paper. If it takes up more paper, it means having to chop down more trees. And so, anyway, if we go 17.5, that gives us a density of 0.99871. That's your theoretical. But you should be able to get 6 sig figs because our table has 6 sig figs in there.
So then what would be my experimental? Would that be?
That would be the calculated mass. That is the mass of the flask, watch glass, and water minus the mass of the flask and watch glass. And that gives you the mass of the water inside the flask. And the volume would be the final volume in the Moore pipette minus the initial volume in the Moore pipette. And then you take the mass divided by the volume, that gives you the density. And so it asks you to calculate the density. It asks you to do 2 things in part A. It asks you to calculate the density based on experimental observations and then look up the density from the data table.
So here I have, 0.9999716 grams per milliliter. That's the density ratio.
That's the theoretical density.
Right. And where I was getting confused was I was able to find the average. Oh, okay, so the mass of water is, let's say, 10.8045.
Yeah.
So then I would subtract the theoretical from that?
No.
That's where I'm getting confused.
The experimental density you calculate from the mass of water divided by the volume of water. That's what we call the experimental density. And that goes here. And so this is the experimental density from the calculation. You plug in here. Minus the theoretical density is from the table. So you go to the density table and you look at your temperature. You said you had 17.5. And that would be 0.99, what was it?
0.9999716.
This goes here. That's your theoretical density. And then you divide it by the theoretical density, which would be the same number here. And then you multiply by 100%.
I see.
That would be your percent error.
So for part B, there's 4 parts, but in 3 parts, the first 3, those are the ones that ask for percent error. It looks like 1 and 2 are asking for the percent error in the volume, and 3 is asking for the density. Because in 1 and 2, like on the actual tables, the only part where it mentions density is just like copying the density from the table to here.
Oh, part B?
Yeah, in part B, like this is the more. It wants us to do that and then calculate volume.
Oh, okay. All right.
And it's like that for 2, and then 3 is density.
All right. All right. Sorry, this is something else. This is the percent error in density. In part B is this. Remember we asked the question, which one is more accurate? The Moore pipette or the volumetric pipette? How can you tell which one's more accurate? You know how you can tell which one's more accurate? By calibrating it. And then how do we calibrate it? Well, I don't know. How do you calibrate a pipette? You know how we calibrate it? We determine this. If we measured, let's say we measured 9.90 milliliters of water dispensed, did we really get 9.90 milliliters of water? How can we tell how many milliliters of water we actually got? All right, so measuring volume is always tricky. And so what's preferred is to measure mass. Measuring mass is simple compared to measuring volume. If you want to measure mass, you just throw it on the balance. How many sig figs can you get by measuring the mass? Well, like say, for example, how many decimal places did we get in measuring the mass? If I measure 1 gram of water, how many decimal places can I get that to?
Is it exactly 1 gram?
If I measure 1 gram of water, how many decimal places can the balance measure to? The expensive balance, the $5,000 balance pre-inflation. I don't know, post-inflation it might be what? $10,000? Who knows?
You get 4 decimal places.
4 decimal places. So if I measure 1 gram of water using a balance, I could get 4 decimal places, so I could get it like 1.000 grams, right? If I measure the volume of water, how many decimal places can I get? Using a burette, which is pretty high precision, or using a pipette, which is pretty high precision, how many decimal places can we get? 2. So if I measure 1 milliliter, which is about 1 gram, I can only get 1.00, that kind of precision, right? And so which one measures much more precisely, a balance or a pipette or burette? A balance. Which one's easier to calibrate, a balance or a pipette? A balance. You just get a, you don't go to France and pick up the kilogram and bring it back. They sell like clones, knockoffs of that. They aren't perfect, but they're good enough. And they're expensive. And so we have calibration masses that we use. And calibration masses, we just calibrate it. How do you calibrate a pipette? Do you go to France and then they have a special thing to calibrate a pipette? No. And so part B is what we call calibration of the pipette. Is it really measuring the volume that it says it's measuring? And so this is how we do it. What we do is we figure out what the volume is of water that was dispensed. How do we calculate the volume of water that was dispensed? We measure the initial and then let it drain and then measure the final. And so we get the volume. Well, okay, that's the volume that the pipette told me I dispensed, but is it really accurate? And so the way that we check the accuracy of the pipette is we compare this to, okay, this would be the experimental volume. We compare this to what we're going to call the theoretical volume, the actual volume. The actual volume is what we're going to do is we're going to take the mass of water. Now, the mass we can measure quite accurately and quite precisely. And so we're going to take the mass of water and then just convert it into milliliters of water using the density. And so this is going to be called the actual or theoretical volume. And so in part B, you're going to be comparing what you think you got versus what you actually got. Does that make sense? And so all we're going to do here is, in this case, the percent error is going to be the experimental minus the actual divided by the actual times 100%. and we're going to say that this should be much more accurate. You know, the volume of water based on the theoretical density based on the mass. I mean, based on both of the mass and the theoretical density. And this is going to tell us the percent error in the Moore pipette. And then we can compare that to the percent error in the volumetric pipette, and which one gives us a smaller percent error should be the one that's more accurate. Okay, other questions? No? So we left off with chapter 2. We're looking at atomic masses, the mass spectrometer, and we're going to look at the mole concept and Avogadro's. We'll do a brief review of the periodic table after that.
One last question about that. For the weights with the 3 coins and some of the weights, I was getting a negative percent difference. I could take the absolute value.
Don't take the absolute value.
But what I found weird was I was getting 0.004%.
It's fine.
That sounded a little too good to be true.
It should be exactly the same. And so it's good. It's hopefully it's small. You know, the
Yeah,
difference.
that's really small. That's because like in Chem 4, I was getting like closer to a larger percent.
Yeah.
Is that common in
No. No, it's because of that particular experiment. What's leading to the error there is just round off error. You know, because you don't really, there's not much room for user error, the experimentalist error, because all you're doing is weighing 3 coins individually and then weighing 3 coins combined. If you weigh 3 coins individually, then that's 3 different measurements, and then you're going to have 3 different round off. The balance has to round off 3 times, and so it does an intermediate round off. I'll talk more about that
But that's
later.
an okay percent error.
Yeah. Some people actually end up with 0. That is, they get the same. It depends on what class you take. A lot of people in physics, they take the absolute values of this. And that way they always get a positive percent error. Chemists don't do that. The reason is chemists want to know what direction the error is. Let's say you're always getting a negative percent error. Let's say you're always getting a negative 1.5% error. Every time you do this, you get a negative 1.5% error. If you're always getting a negative 1.5% error, then you know what that's telling me? It's telling me it's not random. That's not a random error. A random error should be positive, negative, positive, fluctuates, right? We have 2 types of error. We have random error and we have systematic error. If you're always getting a negative 1.5%, that's got to be a systematic error. That systematic error has got to be due to miscalibration. Maybe the balance wasn't properly calibrated, or something else. User error. Each time you're doing, you're always doing it the same wrong way. And so we don't take the absolute value. We want to know, is the error low or the error high? And we expect it to go in both directions, if it's really random. And so don't take the absolute value. All right, today I'm going to finish up chapter 2, and then we're going to start chapter 3, and we'll finally get to the quiz. Yeah, the quiz is very short. How long do you think the quiz will take you? write the formula for 6 acids?
I had a dream last night that, no, seriously, that the quiz included dimensional analysis. He told us to study the acids, and then he gave us that and dimensional analysis. So that was
Why
interesting.
Yeah, that's a great idea.
No.
We agree.
Dimensional analysis is always
Oh,
good to have
yes.
on quizzes, and I can throw in a dimensional analysis problem in there pretty easily. Yeah, that sounds like a nightmare. Was it a nightmare?
It was a nightmare.
All right. Well, you don't have to worry. I mean, this quiz should take, what, less than a minute? Would you say less than a minute? Yeah. All right, so let's take a look at the mole and Avogadro's number. Avogadro's number is given the symbol N sub A. If we're looking at the mole and Avogadro's number, I always start with U. What's the definition of the U? How's the U defined? Are there carbon-12 atoms locked up in a vault in France? That, you can go and collect those carbon-12 atoms and then feed them into your mass spectrometer to calibrate it? No, the definition of the atomic mass unit. Do you know the definition of the kilogram is platinum palladium alloy chunk in France? But they're going to try to change it because it's not accessible to everybody. And it's too valuable. You don't want people touching it, right? You want people touching that? You don't want anybody touching it. It's going to leave fingerprints on there. This is the definition of the kilogram. What's the definition of the U, the atomic mass unit? Is there like a chunk of platinum and palladium in France that weighs exactly 1 U?
No.
Is it possible to have a chunk of platinum and palladium that weighs exactly 1 U? Is that possible? No, it's impossible. Is there anything in the universe that weighs exactly 1 U?
Single carbon
A
12.
12 of
Is there such thing as a 12th of a carbon?
No, I just remember the book saying.
Yeah, it's 1/12 of a carbon atom, but can you find 1/12 of a carbon atom anywhere in the universe? No. So is there something else that weighs exactly 1 U? The carbon atom would be too heavy. What about hydrogen atom? Hydrogen atom's close, but no. It's not going to weigh exactly 1 U. And so what weighs...
N sub A.
These are the ones we buy. These are calibration standards. Like this one, this 5 kilogram calibration weight is $1,158.
Nope.
We don't have that. We gotta look for the cheapest one.
The rice.
Yeah, this is pretty good. Stainless steel, $168. This one's pretty good, $110. We have a little container. It's probably, I think the cost was like $60. There's a bunch of them. This is the real one. International. Look at, they don't even want air to touch it. They have it sealed in some kind of inert atmosphere. So there's no air touching this either. Do they have 1 bell jar, 2 bell jars, 3 bell jars? I'd like to look at it. And then they have this thing. You know, this little tube here, they can hook up a hose to this and then suck out all the gas out of here. And then what they do is they suck out the gas and then they backfill it with inert gas, like inert being a noble gas, probably argon. But it looks like they use multiple gases there to protect it. But if it's like that, nobody can ever use it. So it's not very useful. Even NBC, wow, NBC has a news story, the definition of the kilogram. I guess there's more interest in that than I would have expected, but does NBC have the definition of the atomic mass unit, the U? No. But the definition of the U, or the AMU, is accessible to everyone. And that's because the AMU is based on carbon 12. And what do we know about carbon 12?
Exactly 12.
Yeah. One carbon 12 atom weighs exactly 12U by definition. So somebody just said, okay, let's pick a carbon 12 and we're going to call it 12U. Problem is you can't have 1/12 of a carbon 12 atom. You can't slice it up into 12 pieces. But that's all right. Okay, then based on this, we come up with the definition of the mole. What is the definition of the mole? Yeah, but that came after. What came first? Avogadro's number came after. Let's talk about the mole first, and then we'll talk about Avogadro's number. The mole was defined first, before Avogadro's number was even determined. What is the definition of the mole? In other words, where does 6.022 times 10 to the 23rd come from?
Is it like the amount of atoms of a specific gas take up like 1 meter of space, or
Something like that. Does somebody have it? This is kind of right, but not quite correct.
Was it the grams per U?
Well, we'll get that relationship later. But the mole, this is just arbitrary. Nobody knew what the mole was when they defined it. After they defined it, then they figured out what the mole is. And so what was the definition of the mole?
Do you want me to just read from the book?
No.
No.
You could.
I'm trying to.
You know,
It's worth
I
it.
told you about memory.
Yeah.
Memorizing a passage in the book is more difficult than memorizing it. I mean, if you rephrase it in your own words, then it's a lot easier to memorize because it's in your own words versus reading somebody else's words. So it's a lot harder to memorize other people's words than. So it's better to make your own words.
It's written kind of ugly anyway, so it doesn't matter.
And so basically, to define the mole, like this: in 1 mole of carbon-12 atoms, we'll have exactly 12 grams of carbon-12. And so, in other words, 1 carbon atom weighs 12U. 1 mole of carbon-12 atoms weighs 12 grams. Okay, now comes the challenge. How many atoms are in exactly 12 grams of carbon-12? And so, first we define the U, then we define the mole, and then we determine Avogadro's number. And so they figured out in 12 grams of carbon-12, there must be how many? A lot. And so 6.022 times 10 to the 23rd carbon-12 atoms. And so this is where the strange number comes from. Strange number comes from because they wanted to define it this way. Why did they want to define it this way? They wanted to define it this way so that when you represent the mass, you can use 2 units. So when we look at the table of isotopes here, and we look at the mass of carbon-12, well, we should already know what the mass of carbon-12 is. Here, a carbon-12 has a mass of 12, but we have 2 different units that we could use for this. And so something that has a mass of 12, the reason for defining it this way is this. If we know that carbon-12 is 12.000, it's infinite here because we have infinite sig figs, then what this means is it's exactly 12 grams per mole, or it's 12 U per atom. And so we have 2 units we can use, grams per mole of atoms, or U per single atom. And this holds for everything. So if we go to carbon-13, carbon-13 has a mass of 13.003355. And so there are 2 ways of reading that mass. The first is it's going to be 13.003355 grams per mole of carbon-13, or it's going to be 13.003355 U per single carbon-13. So 1 carbon-13 atom. These will be moles of atoms. And so this is why the Avogadro's number came out weird like that, and it was to define it so that they're numerically the same. Yeah. And so it's actually pretty ingenious. All right, so let's do some calculations. Calculations that involve this mainly dimensional analysis. How much, if I have a cup of water, are all the water molecules in that cup the same? No. Some are going to be heavy, some are going to be light, right, or lighter, heavier. What's the heaviest water molecule in a cup of water? Yeah, 218.2. H2, so how much H2, O18, H2? This is looking at specific isotopes. Here we can just combine it and look at the mass number combined. What's the combined mass number of H2O? This one. It'd be 2 plus 18 plus 2, so it'd be 22. That would be the heaviest. And if the mass number is 22, then the mass is going to be around 22, because the mass number indicates how many protons and neutrons. A proton weighs about 1 U, a neutron weighs about 1 U. Neutrons just slightly heavier. Electrons don't weigh much, so we can ignore those. And so we're going to have about 22 U's worth of mass. But that's not, that's the qualitative mass. Not so precise. So how much H2O18 H2 is in a cup of water? So if you had a cup of water, how much of the heaviest of the heavy water molecules did you consume? All right, so let's go ahead and start as dimensional analysis. We're going to start off with 1 cup of water. Okay, then where should we go? Okay, do you know the conversion from cups to liters? Is that one you should memorize? No. I don't know the conversion. So let's do one that we know.
Do cups to ounces.
We could go from cups to ounces. Do you know how many ounces are in a cup? 8? Okay, let's try that. But then where would we go from ounces?
I did this one.
Should we go from ounces to grams? Do you know how many? And then we got the two ounces. There's something called a fluid ounce, and then there's mass ounce. 16 ounces in a pound, is that 16 ounces fluid or mass or weight?
Trying to get to them.
I don't know. We got to think.
Because we can do milliliters,
Yeah, a cup is 250 milliliters.
That's
A cup is actually 236 milliliters. I think so. And then, do you want to memorize that? No. So we could go from cups to ounces, fluid ounces. Or we could go from cups to do you know how many cups there are in a pint? And so 2 cups in a pint. Do you know how many pints are in a quart? Do you know how many liters are in a quart? No. Do you know how many liters are in a gallon?
Yes.
Yeah. So how many quarts are in a gallon? 4 quarts to a gallon. And then how many liters in a gallon? 3.785 liters in a gallon. We could have gone to ounces and see where we end up, but it's likely we would have dead-ended. All right, so now I have liters of water. Where should I go next? To where? Probably not to grams just yet, because densities are given not in grams per liter. Densities are given in grams per milliliter. So let's go from liters to milliliters. Now I have milliliters of water. From milliliters of water, I can go to grams. What is, well, here, they didn't tell us the temperature. How are we going to get the density if we don't know the temperature? So some people give up. They give up because we're missing a key variable, and the key variable is what the heck is the temperature, because the density changes with temperature. But that's bad. You know, it's not good. At least you should come up with some answer. Even though they didn't tell us the temperature, we can assume the temperature must be reasonable. You know, if somebody were to ask you how much of this is in a cup of water, do you think they're going to specify the temperature? No, they're probably not even going to care. And so they're probably talking about, if they had a cup of water this morning, how much heavy of the heaviest water did they have? And so we'll just assume a reasonable temperature, maybe close to room temperature. Do you know what room temperature is?
25.
Room temperature is taken as 25, but 25 is a little warm, because 25 is around 77 degrees Fahrenheit, 78. And if it's like 77, 78 degrees, that's almost getting to 80 degrees Fahrenheit. It's too warm, isn't that? But 25 is taken as a conventional room temperature. It's more like 20. 20 is comfortable. What about 17, 18, 19? That's cold. That's our lab. I asked them if they could increase the temperature by like 3 degrees Fahrenheit would be nice. Or 3 degrees Celsius would be nice. But we'll see. And so we don't have the temperature. And if this were a test, we don't have the temperature, and we don't have the density table. We might have the density table on a test. If we didn't have the temperature and we don't have the density table, should we give up?
No.
No. You know, coming up with some answer is better than nothing. So what should we use for the density?
1.00.
1.00. Do you think that is... well, that's what we used in one of the homework problems, 1.00. But do you think that's really justified? Let's take a look at the density table. I have it here. And let's say the temperature were 25. Yeah, then if we were to round this to 3 sig figs, what would it round to? It would round to 1.00 or 0.997. This would round to 0.997. So are you going to memorize 0.997? Probably not, because 25 is a bit warm for a lab. The lab's probably going to be more like 20. If the lab is more like 20 degrees C, then that's really 0.998. So should you memorize 0.998? No. In fact, we're not going to memorize any of these. So hopefully they give us the temperature. If they gave us the temperature, then we can just look up what the density is and then use that. But if they don't give us the temperature, then we should estimate it. And this one's a bit too precise. So if we're at 25 and we round this to 2 sig figs, what would it round to? 1.0. If we're at 20 and we round this to 2 sig figs, it would round to. So I think 1.0 is pretty safe. And so if you're going to memorize the density of water under normal conditions, I'd say under normal conditions, the density of water is 1.0. And if we aren't given temperature, then this is safe for a range of temperatures.
I realized from previous science classes, if you ever get stuck, you could make assumptions just to...
Right, to get unstuck.
Yeah.
Because lots of people get stuck, and then all of a sudden it goes blank, and they give up. You shouldn't give up. You know, you should try to come up with some answer, even though it, you know, each time we make an estimate like that, it lowers the precision and accuracy of our final answer. But that's okay, because we don't even know what the temperature is. They never specified it. If the density varied a lot, then the way I handle a type of question like this is I pick a range. I pick what I expect the low temperature to be, and I pick what I expect the highest temperature to be. And if it's in the laboratory, it's going to be a limited range. If it's outside, it'll be a wider range. And then I'll calculate the low, and I'll calculate the high value, and then compare. And so if you aren't given enough data, don't write on the exam, not enough data, you know. You should try to come up with some kind of assumption. I've seen it so many times. Not enough data to solve, therefore I'm not going to solve it.
That's like your engineering course at UCLA, right? They didn't get enough data.
No, they didn't get the equation. All the data was there.
Oh.
Every single variable was there, and so it was even easier than that. I've had a lot of classes where they didn't give enough data, and people left it blank because they're missing. And then they said, well, the instructor screwed the question up. Because the instructor didn't. But when think about it, when you're at a conference, you're just curious. Well, I'm kind of curious. How much of this heavy water did I drink today? Are you going to tell the presenter, you know, well, how much heavy water did I drink today? You know, today's the temperature is this, and the atmospheric pressure is that, and are you really going to specify all the variables? No, it's very rare that somebody specifies. You know, when people ask questions, they don't think, okay, what are all the variables I need to give? You know, they're just curious and they just ask a question. And so that means whoever's answering the question has to specify all the variables. And so a lot of people aren't used to that because in the homework, they don't do that in the homework. In the homework, they give you all the variables or, you know, you can look them up. And so you aren't stuck. But when you're practicing real science, it happens all the time. They don't specify all the variables because maybe the person asking the question doesn't even know what variables to accompany the question with. And so that's a big difference between homework and, you know, working in science. But anyway, we'll continue with this. So now we have grams of water. What should we go next? Yeah, actually we could go to moles of water here. Moles of water. But do I really want to do that? Now, maybe we want to stay at grams. Let me ask you this. Did we calculate the percent natural abundance of H2O18H2? Have we calculated that? No. No. Okay, let's calculate this. The percent natural abundance is, first we'll start off with H2. And what should I write for H2? Hydrogen 2. Yeah. I'm going to write, for H2, I'm going to write 0.0115 over 100. Okay, what should I write for O18? So let me scroll down. O18, I should write
0.205 over 100.
Yeah. Okay, so times 0.205 over 100 times, what should I write for H2? Point 0.015%. 115%. One of these has to be a percentage. Does it matter which one is a percentage? Yeah, so for example, if I wrote 0.0115 as a fraction and then 0.205 as a percentage, would I get the same answer? Yeah, I would get the same answer. It doesn't matter which one. You just have to have one because our unit should be percentage. And so what is the percent natural abundance of H2O18H2? Can somebody calculate it? I didn't bring my calculator. Although I have my phone. .0115 divided by 100 times 0.205 divided by 100 times 0.0115. How many sig figs am I allowed? I'm allowed 3. And so I'll carry one extra. So I'm allowed 3. This one has to be dropped, but we carry it. Times 10 to the minus 9%. Okay, the next question I ask is this. Is that a percent by mass? And so in other words, does this equal 2.711 times 10 to the minus 9 grams of H2 H2O per 100 grams of H2O. So if I have 100 grams of water, that means I have 2.7 times 10 to the minus 9. 10 to the minus 9 is, what is the prefix for 10 to the minus 9? Nano. So in 100 grams of water, does that mean I have 2.7 nanograms of H2O18H2? Is that correct? No. This is wrong. That's because this is not a percent by mass. This is a percent by what?
Abundance.
Yeah, and the percent abundance is by, not by mass, it's by
Number of atoms.
number of molecules, or number of moles. And so it's an atom percent, molecule percent, or mole percent. All these are numbered. And so what it means is this. That means I have 2.711 times 10 to the minus 9 H2O18H2 molecules for every 100 what?
H2O molecules.
Yeah, for every 100 H2O molecules. Or I have 2.711 times 10 to the minus 9 moles, let's write this, moles of H2O18 H2 molecules for every 100 moles of H2O molecules. And so this would be like a dozen. I'd have 2.7 times 10 minus a dozen per 100 dozen. No, mole's just a counting unit. Since water doesn't occur as atoms, atom percent doesn't make sense. So either molecule percent or mole percent for this. And so at this point, I'd like to go from grams of water directly to grams of H2O18H2, but I can't. And so instead, I'm going to have to go from grams of water to what? Moles. So I'm going to go from grams of water to moles of water, but what I need is the molar mass of water. You guys remember how to calculate the molar mass of water? When we're dealing with a mole of water molecules, do you want to look at every single water molecule? There are 9 of them. Do you want to look at... no, what we want to do is we want to just get the average. And so when we do this, we'll take the average mass of a hydrogen. And so the average mass of a hydrogen is either going to be 1.01 to 2 decimal places or 1.008 to 4 sig figs. Depends on if we want 4 sig figs or 2 decimal places. And the oxygen is going to be 16.00. I like to go 2 decimal places. So I keep it like this. And then I'll multiply this one by 2. And so that's going to give me 18.02. The nice thing, this is because the mole, the definition of the mole, there are 2 ways of reading this. That is, there's 18.02 grams of H2O for every mole of H2O molecules. So if I had a mole of H2O molecules, the total mass would be 18.02 grams. Or it would be 18.02 U per H2O molecule. Or I should say 18.02 U of H2O per molecule of H2O. The strange thing is number 2. In nature, will you find a water molecule that weighs exactly 18.02 U or approximately 18.02 U? Is there a water molecule that exists? It turns out no, there isn't. This is the average weight of a water molecule. But nothing, let's say you had 2 pennies. And you got, let's say the average came out to, what does a penny weigh? 2 grams? 1 gram? How many grams did you get for a penny?
Around
2.5? Um, 2.5, 2.4. Did you weigh any other years?
Yeah, three different years.
Okay, what was the other year?
The other, so, the 2020 was 2.5 as well as 2.5219. The first one was 2.5034.
Oh, all right. Not that big of a difference. Well, anyway, let's say you average the weight of a quarter and a penny, and you got some average weight. Are you going to find a coin that weighs that much? No. And so the same thing here. But anyway, we're going to use this first one here. We're going to go from grams to moles. And so let's say 1 mole of water weighs 18.02 grams. And so this gives us moles of water. Once we get moles of water, then we can use this here. But I'm not going to use this because moles are a little bit more abstract. What I'm going to do is I'm going to figure out how many water molecules I have based on this. And so to go from moles of water to the number of water molecules, I'm going to use Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd water molecules per mole of water molecules. All right, the reason I'm doing this is because it's a little easier to visualize. And so I could have used this, but I'm not. I'm going to use this. And so now I have the number of water molecules. And then I know that for every 100 water molecules, I'm going to have 2.711 times 10 to the minus 9 H2O18 H2 molecules. For every 100 H2O molecules. Okay, and that's where I'm going to stop. And so if somebody asks you how much, you can tell them how many molecules of this you just consume. And so let's go ahead with the calculation here. It's going to be 1 divided by 2 divided by 2 divided by 4 times 3.785 times 1,000 times 1 divided by 1802 divided by 18.02 times 6.022 times 10 to the 23rd. My calculator is not functioning correctly. And then we come down here. Times 2.711 times 10 to the minus 4 divided by 100. And I got 2.143 times 10 to the, what did you get?
You got 10 to the 14th.
10 to the 14th? Okay. 10 to the 12th is a trillion, so let's move the decimal over here. I'm going to get 214.3 times 10 to the 12th. Which is going to be 214 trillion. H2O, 18 H2 molecules. So in your cup of water, you just drank 200 trillion of the heaviest water molecules. Did you notice it? That's a lot. 200 trillion molecules is a lot, isn't it? That's a lot. So you might be concerned, if you're consuming that much heavy water, is it bad You might have seen heavy water. Used in the development of a nuclear bomb. Have you heard that?
Mm-hmm.
Yeah, heavy water.
Deuterium oxide.
Right. And so there's actually a pretty good video here. Can you drink heavy water? Have you seen this guy before?
Yeah.
Yeah. This guy he has a bunch of videos called the periodic videos, and a lot of them are really interesting. So you should check it out if you get a chance. He talks about this, the World War II and heavy water. This heavy water was smuggled into the UK. Did you hear about that? And it was kept under the king's bed or something like that. It's pretty interesting. So 200 trillion. Well, 200 trillion, how much does that weigh? How much does 200 trillion water molecules weigh? So here, if I want the mass, these are the two scales that chemists work with, and it depends. If you're working with a cup of water, then for sure you want to use the units grams per mole. If you're working with individual water molecules, then you don't want to use the units grams per mole. You want to use the units U per molecule. If you're working with a large quantity of water, you don't want to worry about individual isotopes. You just want the average. If you're working with individual molecules, you have to worry about isotopes. Because if we're working with individual molecules and we use the mass 18.02 U per molecule, then there's no molecule that weighs that much. And so what we're going to do is we're going to figure out the mass of an H2O18H2 molecule. So how much does an H2O18H2 molecule weigh? Well, it weighs more than the average one, that's for sure. And so we can go ahead and calculate how much that weighs by looking at how much a deuterium weighs. A deuterium weighs 2.014102 U. We have two of those. Actually, I don't need the units here. We don't have to put the units here because there are two different units that we can use. And an O18 weighs, take a look, 17.999160. And so what we'll do is we'll just add it up. We have two of these. So this is going to be 2 times 2.014102 plus 17.99916. And so the actual mass is 22.027. How many sig figs am I allowed? In this case, it's addition mainly, and with addition we look at decimal places. So how many decimal places am I allowed? 6. So this is going to be 27364. So the first thing to notice is that the actual mass is close to the mass number. The combined mass number of H2O is going to be 2 plus 18 plus 2 is 22. And so we expect the actual mass to be close to the mass number. The next thing is we have a choice of 2 units because of whoever devised the definition of the mole made our lives a bit easier. The 2 units that we could use is 22.027364 grams of H2O18H2 per mole of H2O18H2. Or it would be 22.027364 U of H2O18H2 per mole, not per mole, actually per molecule of H2O18H2. So this would be per molecule. Okay, in this case, which one are we going to use? We're going to use this one. We could have used this one if I stopped earlier. Let's see, where would I have stopped? No, actually, we would have to calculate the number of moles. And so we'll go ahead and use this one here. And that is, I know I have 2.143 times 10 to the 12 H2O18 H2 molecules. And I know the mass of each molecule. The mass of each molecule is 22.027364 U. Per molecule. All right, so let's go ahead and calculate this times 2.14 times 10 to the 12th. And I get 47.2. I'm only allowed 3 sig figs now. This is multiplication, and so I'll carry 1 extra. 47.2 sub 0 times 10 to the 12 U. Is that what you guys got?
It's 2.14 grams times 10 to the 12th or 14.
Oh. Yeah, times 14, sorry. Misread. This is times 10 to the 14 U. Okay, is that what you guys got?
Yeah.
Okay. Do you have a good feel for what a U is? You have a good feel for that? It's a lot of U, right? But no, I don't really have a good feel. Let's convert this to grams. Do you know the conversion between U and gram? It's hard to remember. I memorized it in physics. Let me tell you what it is. Maybe I can close this half. Yeah, I must have closed it. All right. This is from the NIST. Have you heard of the NIST before? Physics.nist.gov. NIST is like a government agency. Their budget is in the billions of dollars per year. So it's a fairly rich agency. And NIST stands for the National Institute of Standards and Technology. And so they give reliable data. And they have 1.6605390660 times 10 to the minus 27 kilograms per gram. Or no, grams per U. Kilograms per U. Do you want to remember that number? No. So a lot of people just go 3 sig figs. 1.66 times 10 to the minus 27 kilograms per U, but still that's a number that's hard to remember. So this is why I never remembered it until I figured it out. You know how many U are in a gram? This is easy. 1 gram contains 6.022 times 10 to the 23rd U. And actually, I need to give you enough time for the quiz, so let me stop here.